Mr. Vice-Chancellor, special guests, colleagues, friends, family, and especially all the students of Professor Ozlem, Tastan, Bishop, warm welcome on this quite chilly night, but not as bad as it's been. And of course, also greetings and welcome to those who are online. The Research Award recognizes excellence, innovation, and dedication in research by a current academic at Rhodes University. And tonight, we are privileged to celebrate and learn more about the work of Professor Ozlem, Tastan, Bishop, our 2020 Distinguished Senior Research Awardee from the Department of Biochemistry and Microbiology and Director of the Rhodes Unit in Bioinformatics, or RUBY, as we all know it. Professor Tastan Bishop is a multidisciplinary scientist with a background in physics, mathematics, genetics, biochemistry, and structural biology. She was born and grew up in Istanbul, Turkey. As a child, her father often took her to the bank where he worked. And so she was exposed to large numbers even before she started school. I know our Vice-Chancellor loves this. This is where her love of mathematics blossomed. Her mathematics marks were always at the top of her class, and she was often the teacher to her classmates. After passing university entrance exams, Professor Tastan Bishop was accepted into the physics department at Vice-Chancellor University in Istanbul, one of the top institutions in Turkey. The department was well known to be tough, and the graduation numbers were generally low. While at university, she tutored students who were struggling with high school mathematics and physics. Professor Tastan Bishop's undergraduate curriculum required her to take an extra module each semester, and early on, she chose biology. The tiny and crowded world of cells fascinated her, and she ended up switching from physics to specialize in biology. She completed her master's degree at the same university's Molecular Biology and Genetics Department in 1996. Her first time out of Turkey was when, soon after obtaining her master's degree, she traveled to the Medical Research Council, the MRC in Oxford, on a British Council fellowship. This was to be the first of many fellowships. Others included a Turkish government education scholarship, a Monbusho Research Student Scholarship from the Japanese Ministry of Education, a DFG, that's the German Research Foundation, doctoral fellowship, and an NRF freestanding postdoctoral fellowship, and a Claude Leon Foundation postdoctoral fellowship, which we all know is one of the hardest to get. These allowed Professor Tastan Bishop to pursue her passion for science in different countries, cultures, and education systems. In 2003, she received her PhD degree from the Max Planck Institute for Molecular Genetics and the Free University of Berlin. She undertook postdoctoral studies at the University of Texas, then University of the Western Cape, University of Cape Town, and the University of Pretoria. And after this grand tour of being a postdoctoral fellow, she came to Rhodes, taking up a position as a senior lecturer here in 2009. She was attracted here to establish bioinformatics as a discipline here at Rhodes University, along with the MSc and the PhD programs in bioinformatics that we currently offer. She did well at that, of course, and was promoted to associate professor in 2014 and professor in 2020. Known for her effective postgraduate mentoring, she has graduated 21 PhD graduates and 36 master's graduates. And she currently runs a large group of postgraduate students. Over the years, Professor Tastan Bishop has received several awards, including the South African Society for Biochemistry and Molecular Biology's 2005 prize for the best experimental biology presentation, and the South African Society for Bioinformatics Silver Award in 2022. Here at our university, she has received the Individual Internationalization Award in 2018, has frequently featured in the top 30 researchers list in our annual research report, and of course, the VC's Distinguished Award that we are celebrating tonight. She serves on the editorial boards of Frontiers in Molecular Biosciences, as well as Frontiers in Applied Mathematics and Statistics. She's an advisory board member of the F1000 Research Bioinformatics Gateway, and she was the driving force behind the establishment of the South African Society for Bioinformatics and Computational Biology in 2013, serving as its first president. Professor Tastan Bishop's work is aimed at making an impact on drug discovery by developing approaches and tools to circumvent mutation-related effects in the context of drug resistance, drug toxicity, and efficacy. In the long term, she would like to be known for Afrocentric computational drug discovery research, specifically targeted at improvements in scientific competencies that can lead to better healthcare and stimulate economic growth on the African continent. So it's my great pleasure to invite Professor Ozlem Tastan Bishop to present her Distinguished Senior Research Award lecture.
Thank you, Peter, for this kind introduction. Thank you. First, I would like to share screen. Okay. Vice-Chancellor, Deputy Vice-Chancellor, Deans of various faculties, Deputy Deans, colleagues, students, friends and family, good evening, and perhaps good morning or good afternoon to some of you if you are joining via Zoom from elsewhere in the world. I would like to welcome you all to this public lecture. And thank you for being with me this evening. But before starting, I would like to actually thank Mr. Vice-Chancellor, Prof. Mabizele, for this Distinguished Senior Research Award. I'm deeply honored. This means a lot to me. Thank you. I also would like to thank my international referees making this award possible for me. I hope they are in Zoom and listening to me currently. Okay, so the title of my talk is The 6 Degrees of Computational Drug Design from Social Sciences to Human Health. Most of the time, social sciences and biological sciences are considered to be very different from each other with respect to their research questions, research approaches, and analysis techniques. Today, I will try to take you over a bridge from social sciences to biological sciences, and try to explain actually how we use some of the network analysis concept of social sciences in our drug discovery research projects. Okay, one of the major network analysis concepts of social sciences is 6 degrees of separation, in which the idea that people who may be very unlike one another are connected by a chain of at most 6 mutual acquaintances. This might be already, you might be already thinking that this is not a realistic assumption. I personally cannot imagine myself, for instance, being connected to a random fisherman in Japan or Scottish actor Gerard Butler by 5 other people. It doesn't sound like a fact. It is not exactly known from where this idea is coming or is originated. The earliest reference to this concept of 6 degrees of separation was demonstrated, shown in the short story called Chains in 1929, written by Hungarian author Karintki. Later on, in early 1950s, two scientists, mathematician Manfred Cohen and political scientist Etienne de Solapou, wrote a manuscript called Contacts and Influences. This manuscript was only published after 20 years later, but it basically established many basic concepts of network analysis, including the degree of connectedness. The manuscript was looking at social networking and mathematical consequences. Meantime, a social scientist, Stanley Milgram, actually collaborated with these two scientists and set up the famous experiment called Small World Problem Experiment in 1967. Neither Stanley Milgram nor these scientists actually talked about 6 degrees of separation. Stanley Milgram, for instance, looked at the average path length, but these were the basis of the network analysis. And this term became very famous, very popular. In fact, in 1990, with American playwright John Guare in his play called 6 degrees of separation. Okay, let's look at a small word problem a little bit, designed by Stanley Milgram. The aim was to find the average path length while sending a letter from one place to other. The goal of the experiment was to find a chain of acquaintances linking people in the United States who didn't know one another. And Stanley thought that the start point can be somewhere around Nebraska and end point would be Massachusetts. And he thought that this is basically very distant from each other, but also people were culturally very different from one another. Over many trials, the average number of steps in chains was between 5 and 6. As I indicated, he never used the 6 degrees of separation, but his findings contributed to widespread of this term. Nowadays, this term and network analysis is used by social media, industry, and companies to reach as many clients as possible, to spread a message as widely as possible. Let's look at a little bit social media. In 1994, Kevin Bacon stated in one of the interviews that he had worked with everybody in Hollywood or someone who has worked with them. And this statement inspired three college students, and they invented the famous game 6 Degrees of Kevin Bacon. Okay, so the goal of the game is basically connect any actor to Kevin Bacon through co-stars in movies in as few steps as possible. And as few steps as possible is basically the shortest path concept in network analysis. The term degree in this context means steps. So if we want to connect John Malkovich to Kevin Bacon, we need to go through Dustin Hoffman. They both played in a movie called Death of a Salesman, and Dustin Hoffman played with Kevin Bacon in a movie called Slippers. So if you want to connect Agnes Jovi to Kevin Bacon, we need to go through via Lambert Wilson and Sharon Stone. It means 3 degrees of separation. And there is 4 degrees of separation between Robert De Niro and Kevin Bacon, meaning we need to go through 4 movies. So in graph theory, in network analysis, each of these actors are called a node, And the movies connecting these actors are the edges. Okay, so let's look at my research interest. It has nothing to do with social networking, of course. Our interest in the group is to look at word of proteins as drug targets. And the interactions of amino acid, we also call them residues that make a protein. So now my question is, can we consider amino acids as social groups of people with different roles and interactions? And what happens if proteins mutate, meaning a few amino acids change within a protein? Yes, we can actually extrapolate a network analysis from social sciences or social media to the protein work. Let's think Kevin Bacon as the orthosteric site of protein. So now I need to define what orthosteric site is. Orthosteric site is basically the functional site of a protein. So if protein drug target is an enzyme, then the functional site would be the active site. And you can see here that active site of an enzyme can be divided into two, catalytic site and the binding site. So drug basically binds to active site and reaction occurs in the catalytic site. If the drug target is a receptor, then the functional site would be protein binding site. So most of the drugs that we use in for whatever disease is basically orthosteric drug. And basically these drugs bind to the active site, functional site of a protein and block the activity directly. Okay, let's look at continue with analogy. Can we consider the amino acids like actors? Yes, we can. We can think actors like the nodes of a network. So what I'm showing here is a cartoon and sphere representation of a protein. This protein is called main protease protein from SARS-CoV-2, which is the causative agent of COVID-19. Each of these spheres are the atoms, and different atoms comes together to make amino acids. And some of these amino acids are colored differently to show how they differ from each other. Okay, so in Kevin Bacon game, basically people are directly connected to him. The connection between the actors are not considered. It's not part of the game. But on the other hand, in a protein network, we need to connect the amino acids to each other to get better view. And in this case, we use not 6 degrees of separation, but 6.7 angstrom interaction concept. Okay, let me talk a little bit about how we started looking at residue networks. In 2012, the Wellcome Trust and NIH started to support large number of African genomics groups. And the idea was to identify genetic and environmental basis of human diseases. For that, they targeted to sequence thousands of human genomes from the healthy and disease sick people. And of course, this necessitated further development of bioinformatics capacity in the continent. That's why we have H3 AbioNet, the Pan-African Bioinformatics Network for Africa. So initially, there were lots of groups from Africa in this network, and we were one of them, and we are still one of them. But we were the only structural bioinformatics group in the network. While most of the other groups were concentrating on genome sequencing, identification of variations, as we are the structural bioinformatics group, we thought that we should do something that we know, and which was the proteins. So we decided to develop human protein mutation web server and related tools and approaches to analyze the variations that will be identified. And these variations, if they are in the proteins, they are called missense mutations. In 2013, I went to sabbatical. To most of my time while I was at Sabancı University. Just before leaving Sabancı University, I heard a talk from Prof. Atılgan here, and she was talking about small word communication. And she was talking about how a network can be constructed for the proteins. And that I found it very interesting that time. But the only connection come to my mind between the missense mutation analysis and the network construction when we started looking at the problem seriously in 2016. So I thought that this could be really very useful way of looking at the mutations. So David Brown, my PhD student that time, and I went back to Sabancı University for a week or so to learn the technique from Atılgan's group. Okay, when we were back to home, we started looking at this more and more. And it was very interesting. Residue network interaction during analysis was mainly used for the static structures, even though people were looking at the dynamic features of the proteins. Only there were a handful studies in this topic. And more than that, RINs were not commonly used for the mutation analysis. First of all, proteins are dynamic, they are not static. So we thought that if we want to analyze, do mutation analysis, missense mutation analysis over proteins, we really need to find a way to look at RINs in dynamic way, not static way. And there are two different approaches that we use: normal mode analysis for crude coarse grain calculations and molecular dynamic simulations, which basically we mimic the protein in the cell line environment and look at the behavior of protein in atomic level. Secondly, when we did the controls for RINs, we came to conclusion that static structures might not give consistent results because it would depend on with what structure you are starting, and not every crystal structure was same or the proteins were prepared correctly. Altogether, we put our minds to prepare a protocol, and David and I came with this protocol here and published in 2017. And this protocol was to analyze missense mutations, basically. And the important part here, we proposed to use RINs over the molecular dynamic simulations. So we called it dynamic residue network, DRN analysis, and DRN calculations basically implement the concept of averaging the residue network, interaction network metrics over MD simulations. We also established a tool that year. We called it MD task, and MD task had number of tools, but DRN tool was part of it as well. And to my knowledge, this was the first computational tool of its kind. After we published this, number of other groups in the world came up with their own tools, a variation of DRM with their own names. Okay, so when you calculate a network from a protein, you can extract lots of information by using different metrics. Initially, we were looking at betweenness centrality metrics and something similar to closeness centrality. These metrics basically attribute different values to each of these residues, even though you are looking at the same network. So over the years, we further developed MD Task, and last year we published MDM Task Web. This is the web server version of it, MD Task. And Olivier actually set up number of metrics for this MDM Task Web. So now I'm showing you all these mathematical formulas, but don't get scared. I'm not gonna go through this. In the next slide, I will try to explain some of these metrics in daily life, what it means. My four favorite ones are Betweenness Centrality, Closeness Centrality, Degree Centrality, and Eigen Centrality. So this node here in this given network would have the highest Betweenness Centrality. So Betweenness Centrality looks at basically which node is the most used node in the shortest pathway. So we think that information goes in the protein within a shortest path. So we calculate all the shortest possible paths and see which node has the highest usage. So that node has gatekeeping role, control of information. I would like to make perhaps analogy to group leader. So all the information has to go through group leader before it comes out as a publication. Okay, the second one is closeness centrality, the average of the shortest distances to all other nodes in a graph. So this node would be closest to every other node, and point of rapid diffusion. So analogy, maybe if you want to spread a word as quickly as possible, you need to find the best person can do that, who could distribute a news or a gossip the fastest. That person would have the highest closeness centrality. Degree centrality is the number of edges connected to a node. It means basically the node has lots of connections. Okay, lots of edges connect to that node. So it has direct influence, like a person, the most popular person in a party would have the highest degree centrality because everybody would know and talk to that person. Eigencentrality is a bit more difficult to define, but basically a measure of extent to which a node is connected to influential other nodes, like important or famous people connected to other important and famous people, or not what you know, but who you know is the most important for this node. Okay, so over the years, as I said, we have been working and been further developing this approach. And I will just try to give very brief idea how we are applying this method before going some of the research examples. So we first calculate the network over MD simulations. Let's say we have two proteins, wild type and mutant protein. So it means that we do two MD simulations and calculate the network over two MD simulations, two networks. And from each network, then we calculate the metrics. So last year we showed that it is really good, very informative to basically combine number of networks and get different information together. So let's say we would like to look at BC, CC, EC. It means that we have to now calculate them for each network, mutant protein network and the wild type network. And then we extract the high centrality residues. So what does it mean? Each residues have, it gets some values and we try to extract like top 5% and they are the statistically significant probably in each metric. And then the next step is perhaps to map those residues into protein structure to see what that means. And we have many different ways of looking at it, but perhaps one example is to look at the difference map, meaning that let's say in the presence of mutation, basically what is changing in the protein, what new nodes are introduced. And we also last year showed that some of the nodes keep coming regardless what mutation you have, or it can be also a drug binding, regardless of what is changing in the protein. Those residues are keep coming in the matrix persistently, and we call them persistent hubs. And probably they are really functionally very important as they don't change with the changes in the protein. So basically, this was, I hope I could give a clear explanation about what network is and how we are using. Now, in the second part of my talk, I will be giving some examples of the DRN, starting from genetic diseases. This is actually, it's our very first DRN study. We were trying to see what we can get out of it. Here we looked at renin-angiotensin system. This system is very important for the regulating blood pressure, and any dysfunction of the system can cause the diseases like hypertension, kidney disease, and heart failure. What happens, renin binds to angiotensinogen and cleaves the first 10 residues to make an active protein. It's highly, I found it very interesting to look at this system actually. Each of these human proteins have lots of variations, lots of mutations, hundreds of mutations. But unfortunately, when we looked at it in 2017, we couldn't see any clinical data linked to these mutations. So we decided to go with the interface mutations, thinking that they are between two proteins and they would for sure affect the system. We looked at 25 mutant systems and took them over MD simulations. And after MD, standard thing is to look at root mean square deviation. So what it means is we are looking at conformational change over the MD simulation, meaning how the structure is changing. Conformation means structure, shape, and compared to the first structure. As you can see here, the wild type is behaving, or the mutant system is behaving very differently from wild type. It means that something is going on. So what is happening here is basically in mutant system, two proteins are going apart from each other, while in wild type, it is staying intact. So this is basically due to the mutation, 1-point mutation. Proline is changing to leucine. We have another tool in MD task, shows the contact frequency. And as you can see, in the presence of proline in wild type, there is 100%, almost 100% contact to these two residues, but it is lost, mostly lost in the presence of the mutation. Of course, we did a next step, DRN calculations and Betweenness Centrality. What I'm showing here is the heat map conversion of the data, wild type minus mutant values. So blacks means zero, no change. And these regions shows that there are changes. And it was interesting to see that in all cases, all 25 cases, certain regions were changing. And that was basically when we mapped into the structure and showed in these different colors here was the interface going towards the core of the protein from both sides, from renin here and the angiotensin. And that was quite interesting. A single point mutation was causing quite a bit of change, information change, change in information flow in the protein. And we realized with that we are actually looking at an allosteric effect. Okay, so that was quite exciting. So allostery, what is allostery? I like to define allostery as action at a distance. Okay, the term comes from Greek. Two Greek words, allos, other, alternates, and stereo, solid shapes. So allosteric sites are far from orthosteric sites. Remember, all orthosteric sites, functional sites, we talked about that. And they are far from orthosteric sites, but any perturbation to allosteric site can affect the structure and function of the orthosteric site. And that is called allosteric communication. So I told you at the beginning that there are most of the drugs are orthosteric drugs, but there are also allosteric drugs, and allosteric drugs modify the function of the protein. I'm saying modify specifically because modification can be inhibition, like in orthosteric drugs, but it can be activation. And that is highly important, especially if you are working with rare diseases, because you want to actually, most of the time, activate the protein, not inhibit the protein. There are different ways to perturb an allosteric site. I'm gonna focus on drugs and binding of drug or the mutation, and the mutations called allosteric mutations. I like to give this analogy for the allosteric communication. It looks like Chinese whisper to me. So you give input from one end, and if everybody is hearing clearly and everybody is talking clearly, you would get the same output from the other side. Or domino effects. So you disturb one domino and it follows in the others. But what happens if there's a person with hearing impairment or person not talk clearly? Then the message changes and colonel can become corona. Okay. Or what happens if dominoes were not ordered correctly? So the information flow can stop. So this is basically how allosteric mutations and modulators behave, act. We have roughly 3,500 FDA-approved drugs, and only 19 of them are allosteric. There's a huge difference between allosteric and orthosteric drugs, and this hints at the difficulty of designing allosteric drugs. In fact, the first drug was in 2004. So over the years, we have been working in how to design allosteric drugs because it's absolutely not easy. And we have a number of steps, and we really believe that DRN helps to identify allosteric drugs, allosteric pockets in many different ways. And this year we published, this is an invited review article, we published this, proposed a protocol and explain every steps there. But I would like to take you back to 2018 because this is very historically important publication for us. This is the first study where we combine DRN with other approaches to show that DRN is very handy to identify allosteric regions in a protein. And this was David Penkler's PhD, part of PhD thesis. And then as a next step, when we identify potential allosteric parts, we decided to screen these regions, a C-terminal region of heteroc protein against a South African natural compounds database that we established several years ago. Okay, so I just forgot to tell, heteroc protein 90 is a very famous drug target for cancer research. But basically, the act the inhibitors against active site doesn't work. It causes toxicity. So we need to find alternative ways like allosteric drugs. So this is the active site, and we looked at the C-terminal domain, allosteric regions that we identified. And as a control, we use novabiocin. Novabiocin is a naturally occurring antibiotic. Okay, so this is non-allosteric inhibitor basically for this protein, and it is shown that it destabilizes the dimerization. They basically two of the proteins come together to make a functional protein. What I'm showing here is the heat protein 19 novabiocin complex allosteric inactivation. So basically, it is, we thought that it's inactivating by the opening V-shape opening motion. So we found now a few natural compounds basically doing the same effect or giving the same effect to HSP90. But also interestingly, this was not the aim, but we also found that some of the compounds are actually not inactivating, but activating the protein by closing motion, as you can see here. I will play again. Okay. So this was one of the South African natural compounds. I also would like to talk a little bit about drug resistance mechanism. Drug resistance is a recurrent problem, especially for infectious diseases and especially for our continent, because whatever drug is designed for these infectious diseases, we get resistance. So I believe that the way to get around of it is actually basically perhaps try to understand what the mechanism of these resistance. And for that, I would like to talk about a concept that we are looking at. We talk about allosteric mutations, and so we can analyze them. There is orthosteric site mutations. If drug resistance is caused by that, it's easy to understand because it's basically probably a direct effect to the drug binding. But sometimes we have this collective working mutations. So many of them comes together to make the cause the drug resistance, and we call them collective effect of mutations. And again, in this review article, we talked this year about that. But I will take you again to historically our first publication on this was Olivier's PhD thesis, collaboration with Prof. Bishop from Math Department. Here we looked at HIV protease because we know that HIV protease is a drug target and there are a number of drugs, but whatever drug is designed for this, it causes, after some time, virus gets resistance. So our research question was, is there a common resistance mechanism against all these proteases? We looked at here 8 proteases, drugs. These are the abbreviations of them. But what I would like to tell you here is these red dots are the mutations. This protease active site is here, but mutations are all around. These mutations are collective mutations, not for, one virus resistance, but it shows all together. So what we did here, we took basically 100 highly resistant sequences per drug and 100 hypersusceptible sequences per drug. We work with 8 drugs. It means that we basically started dealing with 1,600 structures, protein drug complexes. And we took them into short MD simulations, and 2 times it was like 6,400 nanosecond. It was millions of CPUs, and CHPC was, what is going on? But okay, so we explained them. Then we did residue network analysis and statistical test. So the outcome was very interesting because we actually show that these mutations collectively doing something, and there's a common mechanism regardless of what protein you are using. There's a common mechanism behind that. So what you are seeing here is, for these are A, B, C, D, E. These are E for each mutations, and left side shows how protein is expanding, and you can see that expansion is in most of the cases the same. So there is lateral expansion, and this shows the contraction, and there's a contraction from the bottom. So it means that protein is, regardless of what drug you are using, is has a similar movement, like expansion and pushing from back. And we hypothesize that this is basically causing dislocation of the drug. So that's why I think there is a common resistance to, no matter what you are designing for HIV protease, and perhaps better ways using allosteric drugs. So from the, of course, this is a hard question to solve, but the harder one is, how do you handle the potential mutations, and how do you design drugs how do you design future drugs? And this brings me to the last part of my question, and to very important question. We know that COVID-19 is continuously, SARS-CoV-2 is continuously evolving, and how do you handle this? This was the first article that we published in 2020. And this was collaborative work with Prof. Kilker from USA. And what we did here, we looked at the drug target and pro, and the mutations, how they are affecting the structure. And to my knowledge, this was the first publication on that, actually looking at the mutations for this protein. And then we have follow-up article proposing how we can handle the mutations while designing inhibitors. We have lots of data. I'm gonna show you only a few things to explain how the structure is changing in the presence of mutations. So this is a protein. It's homodimer, meaning that two of them again comes together to make a functional protein. And this is the reference structure. This is basically the sequence from the Wuhan strain. And this study, I think it was a few months later, we retrieved all the strains, and there were like 50 different sequences with different mutations. And what I'm showing here is the center of mass, how it's changing between these two monomers. You can see that Wuhan strain, protein from Wuhan strain is a very nicely, there is not much difference, okay? But you can see there is, in some of the strains, this center of mass is really very different from the reference one. So it shows us that mutations are affecting the structure one way or the other. But this means that it is evolving for some purposes. And this is the interdomain angles between two proteins, monomers. And this is the Wuhan structure from the Wuhan strain, the structure. And again, you can see in many of the other strains, the protein was behaving totally differently. And this is root mean square deviation. You might remember I was telling at the beginning, we look at the conformational changes over the MD and compare to the start structure. And again, this is our reference protease, and you can see some of the mutations are causing like two different conformations. Okay, the question, how do you design a drug that inhibits a continually evolving protein? That's very difficult. We tried. Okay, we looked at allosteric sites. We identified an allosteric site in this protein, and we looked at the reference protein and identified 6 compounds, potential compounds, again from our South African Natural Compounds database. Then next what we did, and this is not commonly done, unfortunately, in computational drug design, people just identify something for the wild type and that's that. But this was, I think, very interesting. We basically mutated the drug compound, protein drug complex for 50 different strains that we identified and took into short MDs. And this is what you get. These are, if the ligand, how ligand is behaving, this is what you are seeing here. So if this is like intact like that, it's fine, ligand is stable in the protein. But sometimes you get something like that. It means that in the presence of mutations, that ligand is not stable. So it is actually not effective, probably, and something like that. Even though these 6 ligands were very nicely sitting in the wild type, in the mutant cases, especially this one, this ligand was not very happy with the mutations. And the most stable compound for most of the mutant proteins was this one. So of course we went ahead and did in our network analysis, and what I'm gonna show you here is 2 examples from the least stable ligand and the most stable ligand. And this is the reference protein. And this is ligand here. This is the active site. And we were so impressed actually to see that there is actually a lots of communication going on. And you could see that. So allosteric, there is a communication path between allosteric site and the active site. And it was same for this ligand too. But in some of the mutations were basically breaking this communication path, as you can see here. In this case, this communication is lost. And we believe that this mutation, in the presence of this mutation, this ligand wouldn't be really effective. Okay, only a few words in this research. This manuscript is under review. We got actually very good comments. Hopefully soon it's gonna be published. Here we are looking at Omicron sublineages, and this is also the first its own kind. Many people looked at spike protein alone, but here we first time are showing the communication between spike and the human ACE2. So what happens is SARS-CoV-2 binds to human protein ACE2, and that is how it infects the human. So we know that in Omicron there are lots of mutations, and we show that actually, again, these mutations are collectively affecting, working, not single by single. And this is the human protein, and this is the RBD domain. And this is the interface here. And this is the active site. Okay, what I would like to show you, Omicron is just not one lineage. There are, it's continuously evolving. There was BA1, and then BA2, BA3, 10, 12, 15, meaning that 10 mutations, 12 mutations, 15 mutations, and then BA4. Now we have BA.5 that we don't have sequence yet. And interestingly, they are called the same lineage because the mutations are in the same positions. Okay, but mutations differ, but they are always in the same positions. When Victor showed me this results, I fell in love with these results because this is so actually interesting. So what you are seeing here is communication path between the virus protein, the human receptor. Okay, so this is the virus protein, part of virus protein, and this is the part of human receptor. And this is where the active side, but this is receptor. Remember that I said in receptors, protein interaction is very important. So there is obviously clearly, and this is the reference structure. This is Wuhan strain. Okay. So you can see that there is a clear communication going on between a virus protein and the human protein, and it's ending around the active side of the human protein. And there's another short path, but this is the key one. And let's look at the Omicron variants, how it is evolving. And you can see that this communication the path is weakened here, but then suddenly in BA310, it's getting crazy, it's getting more. And it is basically what we are seeing is virus is trying to find a way perhaps to be similar to this communication, and this is BA4, very similar to Wuhan strain, but at the same time introduce mutations so that can infect easier. Okay, so there are many more results in this article, but I will just stop here. So where are we in our research? Okay, we like to actually use shortest path in our calculations, but our research has no short path, and we have long way to go, and it's very long, it's complicated, but it's not alone, as you can see here. Okay, over the years, we have hosted so many students. It's so fun to work with them. We started cleaning them. I still remember how we found the storage place. So happy we were. And Maggie is here. She helped a lot actually cleaning, and then Sharon also cleaning, designing, and setting up. And here we are after 12 years. And over the years, we got lots of collaborators, some past collaborators, some current collaborators. I hope I haven't forgotten any name here. Apologies if I did. And then funders, of course, without funders, we couldn't do any of our research, and CHPC is especially important for us. We couldn't do any of the MD simulations, and everything depends on MD simulations in our research. But also I would like to thank very special thanks to certain people. First of all, Professor Clayton. Peter, thank you so much for being always available and supporting us. Prof. Rick Bernard, he was amazing dean. Without him, we couldn't set up the bioinformatics at Rhodes University. Prof. Hoppe, You are an amazing HOD, Henry. Thank you. Easygoing, always supportive. And then, of course, Prof. Loeb, Jeremy Baxter, Prof. Nigel, Prof. Burton. They, in the last 12 years, they are always with Ruby teaching and unconditionally. I really appreciate your time and help. And then I would like to thank Dr. Werner Janse van Remburg. I'm not sure if he's online. He said he would join. He really has lots of CPUs, and we always finish like halfway through, and he is always understanding and supportive and gives us renewals, and thank you for that. And last but not least, I would like to thank my family, always supporting me. My mom, she's amazing woman, and my late father and my brother and his family, my husband and my child, my sunshine. Well done to me. Okay, thank you. And teşekkür ederim. Prof. Mabizele, I have a new word for you. Teşekkür ederim.
Professor Tastan Bishop, thank you for a most informative, remarkably wide-ranging lecture this evening. The sheer depth and breadth of the knowledge that you have accumulated in the research group is astounding and an inspiration for all of us. Thank you so much. If I can just present you with a very small token of our appreciation. I'm also reliably informed that there are some members of the research unit in bioinformatics who are here this evening and would like to say a few short words.
Prof, well done. In the group, we've always said no one works harder than you. We've seen you put in all those late hours working hard. And growing up, we're always told that hard work pays off. And you've clearly proven it. So we'd like to present this award to our distinguished academic mother and scientific mentor. Thank you, Prof.
I'd like to invite all of the guests present here tonight to please join me in the concourse for some drinks and snacks. Thank you.